Hey folks. So at the beginning of the semester, I gave you a cheat sheet basically for all the variables we'd be using this semester. It's just a way of organizing yourself, and that's exactly what we're going to be doing here. So we're now at the point where we've done quite a few confidence intervals and hypothesis tests, and what conditions we have tell us what confidence interval or hypothesis test to do. And so this particular set of notes is just a way of organizing all of that information. So we want to know what type of variables we have and what our parameter of interest is. We want to know the name of the test statistic and the name of the we want to know the name of the test or the confidence interval and what our test statistic or confidence interval formula is. That just helps us know what numbers we need, and then the conditions that we have to be able to meet to be able to use that procedure. So the first one is the one sample Z test on the proportion. And we have one categorical variable when we're doing that test, and we're interested in testing the population proportion P. The conditions that we have to meet are random sampling, a binomial random variable. Specifically, we have to have independent trials, we have to have a set sample size, and we have to have two outcomes, something happened or it didn't. And then we have to meet the condition of normality using the central limit theorem. But that condition is specifically that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, where p is that value in the null hypothesis. Then we did the one sample Z interval on the proportion. And most of the time we can combine our hypothesis tests and proportions, our hypothesis tests and our confidence intervals. But with the proportion, the conditions are slightly different. So we're going to separate those. This one is one categorical variable, just like the one proportion test. And we are estimating the population proportion, which is P. The one sample Z interval on the proportion is P hat plus or minus Z times the square root of P hat times 1 minus P hat over N. And if you don't know what these variables stand for, that variable sheet that we had at the beginning, you need to pull it out and you may need to add on to it. We have a random sample of our categorical data. We do still have to have a binomial random variable, and that means that we have to show that we have independent trials. We have to have a set sample size, N, and we have to have two outcomes. And then the difference between this confidence interval and the hypothesis test is in how we satisfy normality. It's still the central limit theorem, and it's still that n times p is greater than or equal to 10, but we don't have p, so we have to use p hat. So this one is n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. So this is the difference between the confidence interval and the hypothesis test, is just whether we're using P or P hat. And just a quick reminder, P hat is X over N. All right. The next test that we did was the chi-square test of proportions. And in that case, we have one categorical variable with multiple levels associated with it, at least two or more levels. The parameter of interest is the population proportion, P or P sub I. And this is a chi-square test of proportions. our test statistic is the sum of the I equals 1 to k. That's the number of categories of our observed counts minus our expected counts squared over the expected counts for each of our categories. The conditions here are pretty trivial. We just have to have some random sampling and that all of our expected counts have to be greater than or equal to 5. All right, the next one we did was the chi-square test of independence. And the difference between the chi-square test of independence and the chi-square test of proportions is we have two categorical variables with 2 plus levels each. So each have to have 2 or more possible responses. And our population proportion Pij is really what we're using as our parameter of interest, but we write ho and ha in words for this one just because it's easier. So our test statistic is the chi-square test statistic, and let me actually put the chi-squared in there this time. The chi-square test statistic is the sum of the I equals 1 to row times column of our OIs minus our EIs squared over the EIs. And so it's the exact same test statistic we had up here, which by the way is a chi-square test statistic. But this time we have to do it for all of the combinations of rows and columns. We still just have to have a random sample or 2 random samples if we do it separately for each variable, and all of our EIs have to be greater than or equal to 5, just like the test of proportions. So it's nice that those conditions are the same. We don't have to remember different things. Then we did the one sample t-test and t-interval. And in the one sample t-test and t-interval, we are interested in one numerical variable, and we are specifically testing or estimating the population mean. Our t-test statistic is t equals x bar minus mu over s over the square root of n. And the confidence interval is x bar plus or minus t times s over the square root of n. And again, if you don't remember or know what these variables stand for, go back to your variables and vocab sheet. This is stuff you need to know by now. We do have to have a simple random sample of our numerical data. We do have to show that we have normality. Either we know that this variable is historically normal and we're told so in the problem, or the sampling distribution is of x bar is approximately normal by the central limit theorem. So n is large, specifically n is greater than or equal to 30. Or the graph of our sample data looks normal and you might use a histogram or a QQ plot or even a box and whisker plot there. And then population standard deviation is unknown, so we use S. And then we also started the 2 sample t-tests and confidence intervals. And so in this case, we have 2 variables. Variable 1 is categorical. Variable 2 is numerical. And variable 1 is the explanatory variable, and variable 2 is the response variable. Our parameter of interest is the difference of means. So it's mu1 minus mu2. And the 2 sample t-test or confidence interval, we have both a pooled and a not pooled version. So we're going to do the pooled version right here. And for the pooled version, the test statistic t is x bar 1 minus x bar 2 over SP times the square root of 1 over n1 plus 1 over n2. And technically in the numerator, x bar 1 minus x bar 2 has minus mu1 minus mu2 in the numerator, but remember that we're looking to see if this difference is 0 almost always. So that almost always goes away. Then the confidence interval formula for this same test statistic is x bar 1 minus x bar 2 plus or minus t times the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. And the conditions for this are not trivial. There are a lot of them. The first one is we have random sampling, and we might have one or two random samples. We might have one random sample and we separate by categorical variable, or you may take a random sample of one category and then a random sample from another category. Either one is acceptable. N1 is approximately equal to N2, which means we have approximately equal sample sizes. We do have to show normality. And to show normality, we can be told that our variable is normal or historically normal. The graph of each variable, each numerical variable is normal-ish. Remember, we don't have to be close with normality. We just have to be sort of close with normality here because T is robust to departures from normality. Each sample could be similar in shape with no big outliers. So both of our histograms might be skewed right, but as long as we don't have any major outliers, the t-test will still work here. The other thing we can do is have large samples. And specifically, the central limit theorem is working here. But remember, we don't use 30 here. We can use n1 plus n2 has to be greater than or equal to 40. So as long as together the two samples have more than 40 pieces of data, we can satisfy the condition of normality. So there are lots of ways to satisfy normality here. And then the last condition is that the population standard deviations or population variances are equal. And to show this, we use a rule of thumb where we use our sample standard deviation for category 1 over category 2. That has to be less than 2. And the sample standard deviation of category 2 over sample standard deviation of category 1 also has to be less than 2. And so we have to satisfy those conditions. We have also done the two sample t-test and confidence interval not pooled. I'm going to let you guys fill this one in. This is also called the Welch's test. And then we did the paired t-test and confidence interval. You guys are going to fill these in. And then I want you to notice that there are blank boxes. So as we go through the semester, you can continue to add to this chart so you can sort of keep yourself organized. This is a great way to prepare for the final exam, but it's also something you may want to keep for future semesters when you are doing statistics in other classes to help you think about, all right, what type of hypothesis test or confidence interval do I want to do? All right, that's it, you guys.